Alrighty, the next section here is, the next section of abstract algebra is about performance bottlenecks. So we mentioned earlier, one of the big problems when you're working with very large-scale data on a cluster, doing a lot of parallel processing, is that you can end up with bottlenecks in your workflows. And that's a big problem because you can think of it, suppose you are Twitter and you've got some program that's chunking through the social graph, and maybe most people have a couple hundred followers or something, and so each little chunk that you've got of people versus followers, it's a nice concise piece of data. You can run it out on different parts of the cluster. And your program is chunking along in parallel, and then suddenly you hit Lady Gaga or Justin Bieber, somebody who has tens of millions of followers. That chunk of data is going to take a lot longer to process. So one of the problems is that if you approach it very naively, without the monoids, then you'll have a lot of little pieces that run very quickly and a few big pieces, we call them heavy hitters, that just stick around forever. What that means is your cluster utilization drops to about 0. And that's a big performance hit, a big bottleneck. So going into this then, we talked about aggregates. I'm going to discuss aggregates a lot more. So I want to ask the question, what is an aggregation? And the idea is to think about reporting. You've probably seen SQL queries running on some kind of database to do sums and averages and maxes and different types of counts. These are all aggregate functions. And typically when we're building reporting in SQL, you're using a lot of these. You're probably doing count a whole lot. That's what goes into dashboards, so this is used everywhere. But really you want to think about it is, if you've got big data, you've got 100 million customers, you want to look at a big picture. You want to look at generalizations. You want to look at your aggregate stats day over day or week over week. You want to roll up a lot of log files and look at things in more general terms. Those are aggregates. And that's the hard problem with parallel processing on big data. So one problem, though, is that when you really do get into very large-scale data, SQL may not really work that well. Definitely a lot of people trying to work that out. There's some great projects along those lines. But the thing about SQL is that generally speaking, your costs are going to grow either in terms of time or money. Time to process or the money of getting the frameworks that can do this efficiently or the amount of hardware that it takes to run it efficiently. However, we can leverage functional programming and abstract algebra to define workflows, data workflows that run in parallel at scale and behave very well. And this involves partitioning the data, having the flexibility to partition the data in ways that are convenient for the data as opposed to making it convenient for the code. It has to do with being able to distribute your computation, being able to take your code and parcel it out across your cluster. It has to do with leveraging what we call partial aggregates. That is to say, let the different pieces do chunks of aggregates and then bring them back together. It also has to do with not having just one big loop at the end where you take all the final results and iterate through them, because that's typically where your bottlenecks come in. Again, what I was saying about, you might have a lot of different pieces for the Twitter social graph, but then hit Lady Gaga and you just kind of loop over that for hours. So performance bottlenecks come in, like I say, these 3 flavors here. And they're going to have a lot of impact on cost and network, et cetera. A couple of people who I'll focus on. First one is Avi Bryant, formerly at Twitter. Avi is one of the co-authors of Scalding, the functional programming for big data based on Scala that I mentioned earlier. And he has an excellent presentation called Add All the Things, Abstract Algebra Meets Analytics. This was at the Strange Loop conference last year. And I highly recommend checking out his video, his presentation. I think Avi is a great speaker and really makes a succinct argument for why are we using abstract algebra and how and what's the business case. And I'll go through that in more detail. But the 3 top level items there are, number 1, grouping doesn't matter. So you can take your pieces of data and group them however is convenient in the flow. And that's by leveraging, as we were mentioning before, associativity. Remember, if I have a lot of numbers and I want to add them together, I can choose to put my parentheses anywhere I need to. So I can make the grouping fit the data as opposed to having the data fit the computation. And that's a very key thing. Another point is ordering of the data doesn't matter. This has to do with the property of commutativity. Monoids don't have that, but you get into other kinds of abstract algebra, semigroup structures, and there are more refined definitions of where you do have commutativity. The other part is zeros get ignored. And we'll revisit this a lot, but the long and the short is that when you've got a graph or a sparse matrix, by definition, you're probably going to have a lot of blank space. And we see this in real-world problems. There's going to be a lot of zeros. So can you go ahead and just factor those out in a very quick way, but still be able to run it in parallel? So again, this has to do with how do you make the problem scale? How do you make your code flexible enough to run at scale? Now, someone who worked a lot with Abi, the other co-author of Scalding, is Oscar Boykin, who is at Twitter, one of the lead data scientists there. And he had a talk at Strata SC this year, actually, just in February, where he went through about Scalding and about something called Algebra, the open source that Twitter has released to take advantage of abstract algebra for parallel processing at scale. Oscar has a great presentation, highly recommend it. I'll show some of his examples a little bit later. But there's a couple points we want to stress. One is this law of associativity, monoids. It allows parallelism when you're reducing your data, when you're making your aggregate. And again, it lets you put the parentheses where you want them, what's natural for the data, as opposed to making the data fit the code. And that's part of how Twitter achieves their high ROI, how they build their revenue apps. Number two, lack of associativity, not using the monoids, it actually increases your latency exponentially. So I'll repeat that. Lack of associativity increases latency exponentially. Now, recall that in a lot of businesses, you can measure revenue loss in terms of milliseconds of latency. Certainly in finance, we see that. Advertising, too, in a lot of places. So by leveraging this property of associativity, you can get exponential increases in how fast you can flow. A computational thinking alert. Out of Oscar Boykin's talk at Strata, he showed this one case I'd like to also reiterate here. If you have a lot of numbers, here we've got 16 numbers, and I'll represent them as variables, A, B, C, D, on through LMNOP. I've got 16 numbers, I want to add them together. Now, this is kind of an example in the small. You can think of this maybe being 16 million or 16 billion numbers, which is probably more of what you'd see at Twitter scale apps. But for right now, we'll just look at this. With 16 numbers, if I iterate through them, I add the first two, add the third, add the fourth, add the fifth, on and on and on, then that's going to take me 15 operations. The cost of that is order n minus 1, is what we'd say. So you can measure your latency, how long it takes to do this summation. The cost is 15. Now, if I were to take that same problem and split it into a tree, you can take a look at the top of the tree being the result that you want, all of the numbers summed together. But the very bottom of the tree, on the leaves, you can see each leaf is computing two numbers together. So the idea there is that you've got parallel processing. You can send out each one of those little tasks. There's 16 numbers. There's going to be 8 of those tasks. You can send it out to 8 different processors and run it in parallel. Once those are done, you go up to the next level. You've got 4 partial aggregates that you add together, done on 4 different processors. Add those together, and then the results from there, 2 tasks. The results from there combining into 1 task. Altogether, that's only taking 4 units of time to compute by doing it in parallel. So you've gone from the naive way, taking 15 time units, versus the monoid way, taking 4 time units. So that's order log, well, it's log n, log of 2 is 4. So you get this exponential increase in performance, cutting down your latency by using this approach, leveraging associativity. And so if you want to graph this out, if you take a look at the old school way, latency is shown on red on this graph here, whereas by using abstract algebra, using monoids, et cetera, for your workflows, you can achieve low latency, you can achieve very high performance apps. You can see that the blue curve there is substantially lower, and it also remains much lower as the problem scales. That's exactly what you want. You want your problem to be able to scale out, to be able to run efficiently at scale in parallel. So the big idea there is that in terms of algorithm design, guarantees of associativity in your code allow for distributed computing. You can leverage things like partial aggregates, graph representation, tree representation, etc. Long and short of that is it means less resources need to be spent on things like sorting or windowing the data, because in the old days what we used to do would be to take the entire data set, sort it, which is a big batch job, and that's costly. And then once we've got it sorted, then we can stream through in a very efficient way. What we're seeing now is that by leveraging abstract algebra and writing our code based on functional programming, then we don't have to think about batch processing and sorting and windowing and all. We can just stream through the data as it comes. And the fact is that for real-time apps, oftentimes you don't have the luxury that you have in batch. You can't step back and adjust it before computing. You have to compute it and respond. So you can't anticipate how you're going to need to cut the data up in chunks. You just kind of have to take it as it comes. This means that real-time apps can now respond much more quickly.